December 2023, the Pentagon released a classified assessment that was later leaked to defense journalists. The document contained a single scenario that military planners considered catastrophic. What happens if rare earth element supplies are cut off for 6 months? The answer wasn't gradual degradation of military readiness. It was complete collapse within 90 days. No new F-35 fighters, no precision-guided munitions, no satellite replacements, no communication system upgrades. The world's most expensive military would be frozen in time, unable to modernize or even maintain current capabilities. The document identified the critical vulnerability. Not mining, not stockpiles, but processing capacity. The United States has rare earth ore. It has mines. What it lacks is the industrial infrastructure to transform raw materials into usable components. And that infrastructure, the chemical plants, the separation facilities, the magnet factories, exists almost entirely in one country. This isn't a story about Greenland, though Greenland plays a role. It's a story about how an entire industry vanished from the Western world while nobody was paying attention, creating a strategic weakness more severe than any military defeat could achieve. In 1985, the United States produced 100% of the rare earth elements consumed globally. American mines supplied American factories, which manufactured components for American and Allied militaries. The supply chain was secure, domestic, and under complete Western control. By 2005, the United States produced less than 3% of global rare earths. China had captured 95% of mining and, more critically, nearly 100% of processing capacity. This wasn't a gradual shift. It was an industrial collapse compressed into 2 decades. What happened? The standard explanation focuses on Chinese labor costs and lax environmental regulations. These factors mattered, but they miss the real story. China didn't just undercut Western prices. They systematically dismantled Western processing infrastructure by targeting the most expensive, most technically complex, most environmentally problematic part of the supply chain. Rare earth elements don't exist in pure form underground. They're mixed together in ore, chemically bonded to other materials, and extracting individual elements requires a multi-stage process that looks more like advanced chemistry than traditional mining. First, ore is crushed and ground into powder. Then it's roasted with sulfuric acid at high temperatures, dissolving the rare earths while leaving waste rock behind. The resulting liquid, a toxic soup of dissolved metals, goes through solvent extraction, adding chemicals that selectively bind to specific rare earth elements, allowing their separation. This process repeats dozens of times. Each rare earth element requires slightly different chemical treatment. Neodymium and praseodymium are particularly difficult to separate because they're almost chemically identical. The entire operation produces massive quantities of acidic wastewater, low-level radioactive waste, and toxic sludge. In the 1990s, Western countries began enforcing stricter environmental regulations. Processing facilities faced requirements for lined waste ponds, water treatment systems, and long-term monitoring. These requirements added enormous costs, in some cases tripling or quadrupling processing expenses. China, meanwhile, concentrated rare earth processing in Inner Mongolia, particularly around the city of Baotou. Environmental oversight was minimal. Waste disposal was essentially non-existent. Toxic wastewater flowed into unlined ponds that leaked into groundwater. Radioactive tailings were left in open piles. The environmental destruction was catastrophic. Satellite imagery shows vast toxic lakes surrounding processing facilities. But the strategy worked economically. Chinese processed rare earths sold for half the price of American alternatives, sometimes less. Western processors couldn't compete. One by one, they shut down. Mountain Pass mine in California exemplifies this collapse. Discovered in the 1950s, Mountain Pass became the world's premier rare earth source. During the Cold War, it supplied materials for nuclear weapons, jet engines, and missile systems. At its peak in the 1980s, Mountain Pass produced more rare earths than the rest of the world combined. Then came environmental problems. In the 1990s, radioactive wastewater spilled multiple times, contaminating surrounding desert. California regulators imposed strict requirements and heavy fines. Cleanup costs mounted. Meanwhile, Chinese rare earths flooded global markets at prices Mountain Pass couldn't match while meeting environmental standards. The mine closed in 2002. For the first time since World War II, the United States had zero rare earth processing capacity. Military planners didn't immediately panic. Rare earths were still available, just from China instead of California. The supply chain worked. Weapon systems got their components. Nobody worried about strategic vulnerability because China seemed like a reliable supplier with no reason to disrupt trade. That assumption died in September 2010. The 2010 Senkaku Islands incident revealed the weaponization potential of rare earth control. A Chinese fishing vessel collided with Japanese Coast Guard ships near disputed islands. Japan arrested the captain, standard enforcement procedure. China's response was economically devastating. Rare earth exports to Japan didn't officially stop, but Chinese customs suddenly found documentation problems with every shipment. Cargoes sat at ports. Export licenses were delayed indefinitely. Within weeks, Japanese companies faced supply shortages. The impact cascaded through Japan's industrial economy. Toyota and Honda couldn't manufacture hybrid vehicles without rare earth magnets. Electronics giants like Sony and Panasonic halted production lines. Industrial output collapsed in sectors dependent on rare earth components. Japan released the captain. Chinese customs miraculously resolved all documentation issues simultaneously. Exports resumed normal flow. The entire crisis lasted barely a month, but it fundamentally transformed Western strategic thinking. China had demonstrated that rare earth access could be weaponized without any formal embargo or military action, just bureaucratic delays that were deniable but effective. Pentagon assessments suddenly focused on a question that had seemed academic. What if China did this to the United States? The answer to that question reveals why processing matters more than mining. The United States could theoretically restart Mountain Pass and other mines, or exists underground in viable deposits. But mining ore solves nothing if you can't process it into usable materials. And processing capacity doesn't exist in the West. Not at meaningful scale. Not with the technical expertise needed. Not with the infrastructure to handle toxic waste streams. Mountain Pass did eventually reopen in 2018 under new ownership with Pentagon support. But here's the critical detail. The mine digs ore, concentrates it into a mineral powder, and ships it to China for final processing. America mines rare earths on American soil, then sends them to China to be transformed into usable materials, which are then sold back to American manufacturers. This arrangement solves nothing strategically. If China cuts off access, the United States has ore it cannot use, raw materials without the industrial capacity to process them. Why hasn't America rebuilt processing infrastructure? The costs are staggering and the risks enormous. A modern rare earth processing facility costs $1.5 to $2 billion to construct. Environmental permitting alone can take 5 to 7 years navigating federal and state regulations. Building the physical plant takes another 3 to 5 years. Technical expertise has largely moved to China. Western companies must essentially relearn industrial processes abandoned decades ago. Most critically, China can destroy any new processing facility economically. If a Western company invests $2 billion building processing capacity, China can simply flood global markets with cheap rare earths, crashing prices below operating costs. The Western facility goes bankrupt before achieving profitability. China has done this before. It's how they eliminated competition in the 1990s and 2000s. Private capital won't accept these risks. No rational investor will commit billions to an industry where the dominant competitor can deliberately bankrupt them through predatory pricing, supported by state subsidies. This is why Pentagon funding has become essential. The Department of Defense is now directly investing in rare earth projects, guaranteeing purchases at fixed prices regardless of market conditions. They're treating rare earth production as a defense industrial base issue, requiring government support, not a free market opportunity. Even if America rebuilds processing capacity, a second bottleneck exists: magnet manufacturing. Rare earth elements aren't used in pure form. They're alloyed with other materials and manufactured into magnets, which are then installed in motors, generators, and weapons systems. This manufacturing requires specialized equipment, proprietary techniques, and technical expertise that's concentrated in China and Japan. Neodymium iron boron, NdFeB, magnets, the super-strong magnets essential for electric motors and wind turbines, require precise heat treatment, controlled atmosphere processing, and specialized coating techniques. The manufacturing process is as complex as semiconductor fabrication. China controls approximately 85–90% of global permanent magnet production. Even if Western countries successfully process rare earths, they'd still depend on Chinese manufacturers to transform materials into finished magnets. Japan maintains significant magnet manufacturing capacity, which provides some diversity. But Japan itself depends on Chinese rare earth supplies, creating a dependency chain where Western militaries rely on Japanese magnets made from Chinese materials. The Pentagon's emerging strategy recognizes this multi-layered problem. They're not just funding mines, they're funding the entire supply chain from ore to finished components. This includes processing facilities in the United States and allied nations, magnet manufacturing plants in North America and Europe, research into alternative magnet designs requiring fewer rare earths, recycling programs to recover rare earths from discarded electronics, stockpiles of critical materials as strategic reserves. Each element requires years of development and billions in investment. And all of it remains vulnerable to Chinese economic warfare until Western capacity reaches sufficient scale to survive predatory pricing. While America struggles to rebuild domestic capacity, Australia has emerged as a potential alternative source. Australia contains significant rare earth deposits and, unlike the United States, never completely abandoned the industry. Lynas Corporation operates Australia's primary rare earth mine and maintains processing facilities in Malaysia. This provides a non-Chinese supply source, though at limited scale compared to Chinese operations. But Lynas illustrates the processing challenge even for countries that maintained the industry. Their Malaysian processing plant faced years of political opposition over radioactive waste disposal. Environmental permits were repeatedly challenged. Local communities protested toxic waste storage. The plant operates, but at capacity far below what would be needed to replace Chinese supplies. Australia's government is now funding expansion of rare earth processing, particularly for heavy rare earths like dysprosium that are critical for military applications. But building industrial capacity takes time, measured in decades, not years. This brings us to Greenland, which is often presented as the solution to Western rare earth dependency. The reality is more complicated. Greenland does contain massive rare earth deposits, particularly at Kvanefjeld in the island's south. Geological surveys suggest it's one of the world's largest reserves. If fully developed, Greenland could theoretically supply global demand for decades. But having ore underground doesn't solve the processing problem. Greenland has no processing infrastructure, no industrial base, and a population of 56,000 with no history of large-scale industrial operations. Even if mining began tomorrow, the ore would require processing somewhere, most likely China, which defeats the strategic purpose. Moreover, Greenland faces unique political complications. The island is self-governing, but remains part of the Kingdom of Denmark. Mineral rights belong to Greenland's government, which must approve any mining operations, and Greenland's population is deeply divided over whether mining should occur at all. The specific problem with Kvanefjeld is uranium. The rare earth ore is mixed with uranium and thorium, low-grade but radioactive. Extracting rare earths means processing radioactive material and dealing with radioactive waste. For an island dependent on pristine environment for fishing and tourism, this creates severe concerns. In 2021, Greenland held elections focused almost entirely on the Kvanefjeld mine. The anti-mining party won decisively and quickly passed legislation banning uranium mining, effectively killing the project. This illustrates a broader reality. Even if rare earth deposits exist, actually mining them depends on local politics, environmental regulations, and social acceptance. The West cannot simply find new sources and solve the supply problem. Every potential mine faces years of political battles, environmental assessments, and community opposition. Given the difficulties of new mining and processing, recycling has emerged as a partial solution. Every discarded smartphone, laptop, and electric vehicle contains rare earth elements that could theoretically be recovered and reused. Japan has led in rare earth recycling, driven by necessity after the 2010 supply crisis. Japanese companies have developed processes to extract rare earths from electronic waste, recovering materials that would otherwise sit in landfills. But recycling faces significant limitations. The quantities are relatively small. A smartphone contains less than a gram of rare earths. Collection and processing costs are high, and recycling can only recover materials already in circulation, not meet growing demand as electric vehicle adoption and wind turbine installation accelerate. Studies suggest recycling might eventually supply 15–20% of rare earth demand, but it cannot replace primary production from mining. It's a valuable supplement, not a complete solution. Some researchers point to the ocean floor as a potential rare earth source. Underwater volcanic vents and certain seafloor sediments contain rare earth concentrations, sometimes higher than land-based ores. Deep-sea mining technology is developing rapidly. Several companies have demonstrated pilot projects extracting minerals from the ocean floor. The technology exists, though costs remain extremely high. But deep-sea mining faces massive environmental opposition. Marine ecosystems near proposed mining sites are poorly understood, and the ecological impacts of large-scale ocean floor extraction could be catastrophic. International regulations governing deep-sea mining are still being negotiated, and many nations support moratoriums until environmental impacts are better understood. Even if regulatory and environmental issues were resolved, deep-sea mining faces the same processing bottleneck. Ore extracted from the ocean floor still requires processing in chemical plants, which still largely exist in China. Given the difficulties of rebuilding supply chains quickly, some strategists advocate for massive strategic stockpiles, warehouses filled with rare earth materials sufficient to supply military needs for years during a supply disruption. the United States does maintain a national defense stockpile created during the Cold War to ensure access to critical materials during wartime, but the stockpile's rare earth holdings are minimal and outdated, focused on 1960s military technologies rather than modern weapons systems. Expanding the stockpile sounds simple, but faces practical challenges. How much to stockpile? Which specific rare earth elements? In what form? Raw ore, processed oxides, or finished magnets? Where to store them safely? And how to rotate inventory as military technologies evolve? Moreover, stockpiles address military needs, but not commercial demand. If China cut off rare earth exports, the impact on civilian economy, electric vehicles, wind turbines, electronics manufacturing would be devastating regardless of military stockpiles. Could technology simply eliminate dependence on rare earths? Could researchers develop alternative materials that provide similar properties without strategic vulnerability? Significant research is pursuing this goal. Scientists are exploring alternative permanent magnet designs using more abundant materials. Some promising results have emerged, particularly for lower performance applications. But physics imposes hard limits. Rare earth magnets are so powerful because of fundamental quantum mechanical properties of rare earth elements' electron configurations. No other materials currently known can match these properties. For the highest performance applications, military systems, advanced electric vehicles, large wind turbines, rare earth magnets may have no viable substitute. Research continues and breakthroughs are possible, but betting national security on theoretical future technology rather than securing current supply chains is strategically risky. Understanding China's rare earth dominance requires recognizing it's not just about controlling processing, it's about controlling every step from mine to finished product. China has systematically built vertical integration, mining operations across China and investments in foreign mines, processing facilities concentrated in Inner Mongolia, magnet manufacturing plants, motor and generator assembly, final products like electric vehicles and wind turbines. This structure means China doesn't just supply raw materials, they increasingly supply finished products. They're moving up the value chain from selling rare earth oxides to selling electric vehicles that contain rare earth components. For importing nations, this creates a choice: buy rare earths and build domestic manufacturing, or buy finished products and lose domestic industries entirely. Many countries are choosing the second option because it's economically easier, but it makes them completely dependent on Chinese supply chains. For Pentagon planners, this situation creates a strategic nightmare. Modern weapon systems are so complex, require so many rare earth components, and depend on such specialized supply chains that rebuilding domestic capacity would take decades and cost hundreds of billions of dollars. An F-35 fighter contains hundreds of pounds of rare earth materials distributed across dozens of components. The targeting system, radar, communications, flight controls, and propulsion all require rare earth elements. These aren't simple components that can be swapped out. They're deeply integrated into systems designed around specific material properties. If rare earth supplies were cut off, the United States couldn't build new F-35s. Eventually, it couldn't maintain existing aircraft as components failed and replacements weren't available. The same applies to Navy ships, Army, communication systems, satellites, and precision-guided weapons. The military solution currently pursued involves guaranteed contracts, Pentagon agreements to purchase rare earths at fixed prices from domestic sources, removing market risk, direct investment. Defense Production Act, funding for mines and processing facilities, allied cooperation, working with Australia, Canada, and European partners to diversify supply, stockpiling, building reserves of critical materials for short-term disruptions, substitution research, funding development of alternative technologies requiring fewer rare earths. But all of these are long-term strategies. In the short term, the next 5 to 10 years, Western militaries remain dependent on Chinese supply chains. Ironically, the push toward renewable energy accelerates rare earth dependency. Wind turbines and electric vehicles require far more rare earths than fossil fuel alternatives. A single large wind turbine contains 1,000 pounds of rare earth materials. An electric vehicle uses 2 to 5 pounds, compared to essentially zero in traditional cars. As nations commit to renewable energy targets and electric vehicle mandates, rare earth demand is projected to increase 400 to 600% by 2040. This creates a painful paradox. Addressing climate change requires technologies that deepen dependency on Chinese-controlled supply chains. The renewable energy transition is simultaneously an energy transition and a rare earth transition. Some environmental advocates argue for accepting this dependency, prioritizing climate action over supply chain concerns. Others worry that giving China such enormous leverage over energy infrastructure creates security risks that outweigh environmental benefits. There's no easy resolution. Climate change demands rapid renewable energy deployment, but that deployment creates dependencies that could become weapons in future geopolitical conflicts. Return to that leaked Pentagon assessment from December 2023. The scenario it modeled wasn't hypothetical warfare. It was a trade dispute that escalated to supply chain disruption. In the model, a crisis over Taiwan leads to US sanctions on Chinese technology companies. China retaliates by restricting rare earth exports to the United States and allies. The restriction isn't a total embargo. That would violate WTO rules and create too much international backlash. Instead, it's bureaucratic delays, export licensing complications, and technical difficulties in fulfilling orders. Within 30 days, US defense contractors report component shortages. Weapons production slows. Within 60 days, production lines halt for systems requiring rare earth components. Within 90 days, even maintenance and repair of existing equipment becomes problematic as spare parts deplete. The civilian economy faces similar cascades. Electric vehicle production stops. Wind turbine installation halts. Electronics manufacturers ration components, creating consumer shortages. Stock markets crash as companies report inability to fulfill orders. The United States has rare earth ore. It has mines. It has stockpiles of some materials. But it lacks the processing infrastructure to transform ore into usable components at necessary scale and speed. The industrial capacity vanished decades ago and cannot be rebuilt in weeks or months. That's the scenario that keeps strategists awake. Not a military attack they can defend against, but an economic disruption that reveals industrial capabilities were systematically dismantled while nobody was watching. Addressing this vulnerability requires accepting uncomfortable realities. First, there are no quick fixes. Rebuilding processing infrastructure takes decades, not years. Any strategy must be sustained across multiple presidential administrations and shifts in congressional priorities. Second, it will be expensive. Estimates suggest $50–100 billion to rebuild complete supply chain capacity from mining through finished components. That's similar to the cost of a few aircraft carriers. Not impossible, but requiring sustained commitment. Third, it requires accepting environmental trade-offs. Rare earth processing is toxic and messy. Building domestic capacity means accepting pollution and environmental risks currently exported to China. The question is whether environmental damage in the United States is preferable to strategic dependence on China. Fourth, government intervention is essential. Private markets won't solve this because the economics don't work when China can destroy competition through predatory pricing. This requires government funding, guaranteed contracts, and strategic protection, treating rare earths like the defense industry, not consumer goods. Fifth, international cooperation is critical. The United States cannot solve this alone. Allied cooperation with Australia, Canada, Japan, and European nations can distribute investment costs and create redundant supply chains that are harder for China to disrupt. This isn't a conflict that makes headlines. No missiles launch, no troops deploy, no dramatic incidents generate news coverage. Instead, it's chemical plants closing, technical expertise emigrating, and industrial capacity evaporating while attention focuses elsewhere. But the strategic implications are profound. China has achieved supply chain dominance that gives them enormous leverage over Western economies and militaries. They accomplished this not through military force, but through patient industrial strategy executed over decades, while Western nations pursued short-term economic efficiency. Reversing this requires similar patience and strategic thinking. It requires recognizing that some industries are too strategic to abandon regardless of economic efficiency. It requires accepting that comparative advantage theory, the idea that nations should specialize in what they do best and trade for everything else, has limits when everything else includes materials essential for national security. The competition over rare earths isn't really about rocks and chemicals. It's about whether Western nations maintain the industrial capacity to equip their militaries and power their economies independently, or whether they become structurally dependent on a strategic rival who has already demonstrated willingness to weaponize that dependence. When historians write about 21st century geopolitics, they may identify this moment, when the West allowed processing infrastructure to vanish, as the turning point where strategic balance fundamentally shifted. Not through military defeat, but through industrial surrender that nobody recognized as surrender because it happened quietly, incrementally, invisibly. The question now is whether recognition leads to action, whether the leaked Pentagon assessment from December 2023 becomes a footnote about a crisis that was addressed in time, or a harbinger of a strategic catastrophe that nobody prevented because the threat seemed too technical, too boring, too industrial to demand attention until it was too late to fix. Every smartphone, every wind turbine, every electric vehicle is a small reminder of this hidden vulnerability. And every day that passes without rebuilding processing infrastructure is another day when the strategic balance depends on Chinese supply chains that could become Chinese leverage whenever geopolitical interests demand it.